Ada is a structured, statically typed, imperative, wide-spectrum, and object-oriented high-level computer programming language, extended from Pascal and other languages. It has built-in language support for explicit concurrency, offering tasks, synchronous message passing, protected objects, and non-determinism. Ada is an international standard. The current version is defined by ISO IEC 8652-2012. Ada was originally designed by a team led by Ichbiah of CII Honeywell Bull under contract to the United States Department of Defense from 1977 to 1983 to supersede the hundreds of programming languages then used by the DoD. Ada was named after Ada Lovelace, who is credited as being the first computer programmer. Features: Ada was originally targeted at embedded and real-time systems. The Ada 95 revision, designed by S. Tucker Taft of Intermetrics between 1992 and 1995, improved support for systems, numerical, financial, and object-oriented programming. Notable features of Ada include strong typing, modularity mechanisms, runtime checking, parallel processing, exception handling, and generics. Ada 95 added support for object-oriented programming, including dynamic dispatch. The syntax of Ada minimizes choices of ways to perform basic operations, and prefers English keywords to symbols. Ada uses the basic arithmetical operators plus, dash, asterisk, and slash, but avoids using other symbols. Code blocks are delimited by words such as declare, begin, and end, whereas the end is followed by the identifier of the block it closes. In the case of conditional blocks, this avoids a dangling else that could pair with a wrong nested if expression in other languages like C or Java. Ada is designed for development of very large software systems. Ada packages can be compiled separately. Ada package specifications can also be compiled separately without the implementation to check for consistency. This makes it possible to detect problems early during the design phase, before implementation starts. A large number of compile time checks are supported to help avoid bugs that would not be detectable until runtime in some other languages or would require explicit checks to be added to the source code. For example, the syntax requires explicitly named closing of blocks to prevent errors due to mismatched end tokens. The adherence to strong typing allows detection of many common software errors either during compile time, or otherwise during runtime. As concurrency is part of the language specification, the compiler can in some cases detect potential deadlocks. Compilers also commonly check for misspelled identifiers, visibility of packages, redundant declarations, etc., and can provide warnings and useful suggestions on how to fix the error. Ada also supports runtime checks to protect against access to unallocated memory, buffer overflow errors, range violations, off-by-one errors, array access errors, and other detectable bugs. These checks can be disabled in the interest of runtime efficiency, but can often be compiled efficiently. It also includes facilities to help program verification. For these reasons, Ada is widely used in critical systems, where any anomaly might lead to very serious consequences, for example, accidental death, injury or severe financial loss. Examples of systems where Ada is used include avionics, railways, banking, military and space technology. Ada's dynamic memory management is high-level and type-safe. Ada does not have generic or untyped pointers. Nor does it implicitly declare any pointer type. Instead, all dynamic memory allocation and deallocation must take place through explicitly declared access types. Each access type has an associated storage pool that handles the low-level details of memory management. The programmer can either use the default storage pool or define new ones. It is even possible to declare several different access types that all designate the same type but use different storage pools. Also, the language provides for accessibility checks, both at compile time and at runtime, that ensures that an access value cannot outlive the type of the object it points to. Though the semantics of the language allow automatic garbage collection of inaccessible objects, most implementations do not support it by default, as it would cause unpredictable behavior in real-time systems. Ada does support a limited form of region-based memory management. Also, creative use of storage pools can provide for a limited form of automatic garbage collection, since destroying a storage pool also destroys all the objects in the pool. Ada was designed to resemble the English language in its syntax for comments. A double dash, resembling an em dash, denotes comment text. Comments stop at end of line, so there is no danger of unclosed comments accidentally voiding whole sections of source code. Comments can be nested, prefixing each line with, or skip all that code, while being clearly denoted as a column of repeated, down the page. There is no limit to the nesting of comments, thereby allowing prior code, with commented out sections, to be commented out as even larger sections. All Unicode characters are allowed in comments, such as for symbolic formulas. To the compiler, the double dash is treated as end of line, allowing continued parsing of the language as a context-free grammar. The semicolon is a statement terminator, and the null or no operation statement is null. A single without a statement to terminate is not allowed. Code for complex systems is typically maintained for many years, by programmers other than the original author. These language design principles apply to most software projects, and most phases of software development, but when applied to complex, safety-critical projects, benefits in correctness, reliability, and maintainability take precedence over costs in initial development. Unlike most ISO standards, the Ada language definition is free content. Thus, it is a common reference for Ada programmers and not just programmers implementing Ada compilers. Apart from the reference manual, there is also an extensive rationale document which explains the language design and the use of various language constructs. This document is also widely used by programmers. When the language was revised, a new rationale document was written. One notable free software tool that is used by many Ada programmers to aid them in writing Ada source code is the NAT Programming Studio. History: in the 1970s, the U.S. Department of Defense was concerned by the number of different programming languages being used for its embedded computer system projects, many of which were obsolete or hardware-dependent, and none of which supported safe modular programming. In 1975, a working group, the High Order Language Working Group, was formed with the intent to reduce this number by finding or creating a programming language generally suitable for the department's requirements. The result was Ada. The total number of high-level programming languages in use for such projects fell from over 450 in 1983 to 37 by 1996. The HOLWG Working Group crafted the Steelman Language Requirements, a series of documents stating the requirements they felt a programming language should satisfy. Many existing languages were formally reviewed, but the team concluded in 1977 that no existing language met the specifications. Requests for proposals for a new programming language were issued and 4 contractors were hired to develop their proposals under the names of Red, Green, Blue and Yellow. In April 1978, after public scrutiny, the Red and Green proposals passed to the next phase. In May 1979, the Green proposal, designed by Ichbiah at CII Honeywell Bull, was chosen and given the name Ada after Augusta Ada, Countess of Lovelace. This proposal was influenced by the programming language LIS that Ichbiah and his group had developed in the 1970s. The preliminary Ada reference manual was published in ACM's SIGPLIN notices in June 1979. The military standard reference manual was approved on December 10, 1980, and given the number MILSTD 1815 in honor of Ada Lovelace's birth year. In 1981, C.A. Ahor took advantage of his Turing Award speech to criticize Ada for being overly complex and hence unreliable, but subsequently seemed to recant in the foreword he wrote for an Ada textbook. Ada attracted much attention from the programming community as a whole during its early days. Its backers and others predicted that it might become a dominant language for general-purpose programming and not just defense-related work. Ichbiah publicly stated that within 10 years, only 2 programming languages would remain, Ada and Lisp. Early Ada compilers struggled to implement the large, complex language, and both compile time and runtime performance tended to be slow and tools primitive. Compiler vendors expended most of their efforts in passing the massive, language conformance testing, government-required ACVC validation suite that was required in another novel feature of the Ada language effort. The first validated Ada implementation was the NYU Ada Ed Translator, certified on April 11, 1983. NYU Ada Ed is implemented in the high-level set language SETL. In 1987, the U.S. Department of Defense began to require the use of Ada for every software project where new code was more than 30% of result, though exceptions to this rule were often granted. By the late 1980s and early 1990s, Ada compilers had improved in performance, but there were still barriers to full exploitation of Ada's abilities, including a tasking model that was different from what most real-time programmers were used to. The Department of Defense Ada mandate was effectively removed in 1997, as the DoD began to embrace COTS technology. Similar requirements existed in other NATO countries. Because of Ada's safety-critical support features, it is now used not only for military applications, but also in commercial projects where a software bug can have severe consequences, for example avionics and air traffic control, commercial rockets, satellites and other space systems, railway transport and banking. For example, the fly-by-wire systems software in the Boeing 777 was written in Ada. The Canadian Automated Air Traffic System was written in 1 million lines of Ada. It featured advanced distributed processing, a distributed Ada database, and object-oriented design. Ada is also used in other air traffic systems, for example the Ichbiah Euro unregistered trademark S Next Generation Interim Future Area Control Tools Support Air Traffic Control System is designed and implemented using Spark Ada. It is also used in the French TVM and cab signaling system on the TGV high-speed rail system, and the metro suburban trains in Paris, London, Hong Kong and New York City. Standardization: the language became an ANSI standard in 1983, and without any further changes became an ISO standard in 1987. This version of the language is commonly known as Ada 83, from the date of its adoption by ANSI, but is sometimes referred to also as Ada 87, from the date of its adoption by ISO. Ada 95, the joint ISO-ANSI standard was published in February 1995, making Ada 95 the first ISO standard object-oriented programming language. To help with the standard revision and future acceptance, the U.S. Air Force funded the development of the NAT compiler. Presently, the NAT compiler is part of the GNU Compiler Collection. Work has continued on improving and updating the technical content of the Ada programming language. A technical corrigendum to Ada 95 was published in October 2001, and a major amendment, ISO IEC 8652-1995/1/2007 was published on March 9, 2007. At the Ada Europe 2012 conference in Stockholm, the Ada Resource Association and Ada Europe announced the completion of the design of the latest version of the Ada programming language and the submission of the reference manual to the International Organization for Standardization for approval. ISO IEC 8652-2012 was published in December 2012. Other related standards include ISO 8651-3 Information Processing Systems a Euro Computer Graphics a Euro Graphical Kernel System Language Bindings a Euro Part 3, Ada. Language Constructs. Ada is an ALGOL-like programming language featuring control structures with reserved words such as if, then, else, while, for, and so on. However, Ada also has many data structuring facilities and other abstractions which were not included in the original ALGOL 60, such as type definitions, records, pointers, enumerations. Such constructs were in part inherited or inspired from Pascal. Hello, world. In Ada, a common example of a language's syntax is the Hello World program. This program can be compiled by using the freely available open-source compiler NAT, by executing data types, Ada's type system is not based on a set of predefined primitive types but allows users to declare their own types. This declaration in turn is not based on the internal representation of the type but on describing the goal which should be achieved. This allows the compiler to determine the suitable memory size for the type, and to check for violations of the type definition at compile time and runtime. Ada supports numerical types defined by a range, modulo types, aggregate types, and enumeration types. Access types define a reference to an instance of a specified type. Untyped pointers are not permitted. Special types provided by the language are task types and protected types. For example, a date might be represented as. Types can be refined by declaring subtypes. Types can have modifiers such as limited, abstract, private, etc. Private types can only be accessed and limited types can only be modified or copied within the scope of the package that defines them. Ada 95 adds additional features for object-oriented extension of types. Control structures. Ada is a structured programming language, meaning that the flow of control is structured into standard statements. All standard constructs and deep-level early exit are supported, so the use of the also supported goto commands is seldom needed. Packages, procedures and functions. Among the parts of an Ada program are packages, procedures and functions. Example, package specification. Package body. This program can be compiled, for example, by using the freely available open-source compiler NAT, by executing. Packages, procedures and functions can nest to any depth and each can also be the logical outermost block. Each package, procedure or function can have its own declarations of constants, types, variables, and other procedures, functions and packages, which can be declared in any order. Concurrency. Ada has language support for task-based concurrency. The fundamental concurrent unit in Ada is a task, which is a built-in limited type. Tasks are specified in two parts. The task declaration defines the task interface. The task body specifies the implementation of the task. Depending on the implementation, Ada tasks are either mapped to operating system tasks or processes, or are scheduled internally by the Ada runtime. Tasks can have entries for synchronization. Task entries are declared in the task specification. Each task entry can have one or more accept statements within the task body. If the control flow of the task reaches an accept statement, the task is blocked until the corresponding entry is called by another task. Task entries can have parameters similar to procedures, allowing tasks to synchronously exchange data. In conjunction with select statements, it is possible to define guards on accept statements. Ada also offers protected objects for mutual exclusion. Protected objects are a monitor-like construct, but use guards instead of conditional variables for signaling. Protected objects combine the data encapsulation and safe mutual exclusion from monitors, and entry guards from conditional critical regions. The main advantage over classical monitors is that conditional variables are not required for signaling, avoiding potential deadlocks due to incorrect locking semantics. Like tasks, the protected object is a built-in limited type, and it also has a declaration part and a body. A protected object consists of encapsulated private data, and procedures, functions and entries which are guaranteed to be mutually exclusive. A task calling a protected object is blocked if another task is currently executing inside the same protected object, and released when this other task leaves the protected object. Blocked tasks are queued on the protected object ordered by time of arrival. Protected object entries are similar to procedures, but additionally have guards. If a guard evaluates to false, a calling task is blocked and added to the queue of that entry. Now another task can be admitted to the protected object, as no task is currently executing inside the protected object. Guards are re-evaluated whenever a task leaves the protected object, as this is the only time when the evaluation of guards can have changed. Calls to entries can be recalled to other entries with the same signature. A task that is recalled is blocked and added to the queue of the target entry. This means that the protected object is released and allows admission of another task. The select statement in Ada can be used to implement non-blocking entry calls and accepts, non-deterministic selection of entries, timeouts and aborts. The following example illustrates some concepts of concurrent programming in Ada. Pragmas. A pragma is a compiler directive that conveys information to the compiler to allow specific manipulation of compiled output. Certain pragmas are built into the language while other are implementation-specific. Examples of common usage of compiler pragmas would be to disable certain features, such as runtime type checking or array subscript boundary checking, or to instruct the compiler to insert object code in lieu of a function call. See also, APSE a specification for a programming environment to support software development in Ada, Jovial an earlier U.S. military programming language, PLSQL and PLPGSQL, Ravenska Profile, Spark a programming language consisting of a highly restricted subset of the Ada, annotated with meta information describing desired component behavior and individual runtime requirements, Strawman Proposal, VHDL a hardware description language originally developed at the behest of the U.S. Department of Defense that borrows heavily from Ada in both concepts and syntax, comparison of programming languages, list of programming languages, references. International Standards, ISO IEC 8652, Information Technology Programming Language ISO Ada, ISO IEC 15291, Information Technology Programming Language ISO Ada Semantic Interface Specification, ISO IEC 18009, Information Technology Programming Language ISO Ada, Conformity Assessment of a Language Processor, IEEE Standard 1003.5b 1996, the POSIX Ada Binding, Ada Language Mapping Specification, the CORBA IDL to Ada Mapping, Rationale. These documents have been published in various forms including print. Jean D. Ichbiah, John G. P. Barnes, Robert J. Firth and Mike Woja, Rationale for the Design of the Ada Programming Language, 1986. John G. P. Barnes, Ada 95 Rationalia the Languagia the Standard Libraries, 1995. John Barnes, Rationale for Ada 2005, 2006. Books. Archives, Ada Programming Language Materials, 1981 1990. Charles Babbage Institute, University of Minnesota, Minneapolis. External links, Ada Programming Language Ada at DMOZ, ACM SIG Ada Europe Organization, ISO Home of Ada Standards, interview with S. Tucker Taft, maintainer of Ada.